So now let's finish off this Foner's condition. So last time we proved that the existence of approximate invariant mean will imply the Foner's condition. The last two are basically the Foner's condition implies the Foner's net, and it then implies immutability. Those are kind of easier. So first of all, let's assume that they satisfy the Foner's condition. Then I want to construct a Foner's net. Well, I can just index over all the finite sets, say all the E finite, and let's just say, well, finite subset inside G, of course, and you can pick your epsilon of E that just goes to 0. So for example, you take the epsilon E to be 1 over the number of elements, and by the Foner's condition, there exists a finite subset, say f of E, finite, so that for every S inside your E, the S of Fe set difference with the Fe divided by Fe, of course, that's going to be less than epsilon E. That's for all S inside your set, this finite set E. Because as your E just moves along this net, this E will just contain everything. So immediately you have, when you take the limit over this net of the S of Fe's difference Fe divided by all of the Fe, that's just going to be equal to 0. Okay, so you immediately have a Foner's net. And to show that the Foner's net will imply the immutability. So if you let your mu alpha to be just what do you expect them to be? So for each of these F alpha, the Foner's net, is kind of nice in the sense that when you translate it, it doesn't move too much. So you just consider the mean using these F alpha. Okay, so 1 over F alpha, you normalize it and you do characteristic function. That's going to be inside the probability. Actually, it's finite probability over G. Okay, and if you consider all the left translation, so S dot the mu alpha minus the mu alpha, there's one norm. This is essentially just when you translate it, it's still a 1 over alpha times the characteristic function of something. And this is essentially the characteristic function of the left translation of the F alpha. And the set difference is just basically tells you, well, you're taking the difference of two characteristic functions. So the one norm is essentially the number of elements in their set difference. Of course, normalize it by the weight, this 1 over F alpha. And then you know these are going to go to 0. So now you just consider all of these mu alpha that's inside the probability of G, which is weak star dense in M of G. M of G is weak star compact, so M of G is weak star compact. So we can pick a weak star cluster point of these mu alpha. Let's call it mu. Then this mu is going to be left invariant. Okay, so the S dot mu minus mu, that's just going to go to 0. Okay, so that's going to 0 for all S inside G. That just follows from the Foner's condition. So your mu is your left invariant mean. Okay, so this finished the proof that it's actually amenable. So let's just take a quick example. So the first example you can have is that the set of integers is amenable. Okay, so this is certainly not a compact group, but this one is amenable. Well, the reason is that you can find a really nice Foner's net. Okay, the reason is that if you consider the Fn to be basically all the things from negative n to positive n, okay, and you can think about for every fixed k inside your integer, so let's say these are all the integers. So if you fix a k inside the integer, and you consider the translation of these fn with k, so k with fn, and you set difference with the fn, okay? So, well, you can, this basic combinatorics, you shift it, well, let's just say k is greater than 0. So what you end up with is that, well, what's in the shift is that, well, on the positive side, you have n plus 1, n plus 2, up to n plus k. On the negative side, you have a negative n minus, well, a negative 1, negative n plus 1, and so on. So this set difference is always equal to k. and it's now related to the number, well, it's going to be really small compared to the number of elements in Fn, which is 2n plus 1. Okay, so you divide the Fn, so this is divide Fn, that's going to goes to 0 as n goes to infinity. So that just shows that the set of all integers is amenable. Okay, so that's an easy application of the Foner's condition. In fact, we're going to show that all abelian groups are going to be amenable. Following from the Foner's condition, there's really a nice class of groups that's going to be amenable. It's called the sub-exponential growth. So let me give you the definition first. First of all, let's clean up some notation. So if you have an S contained in G that's finite, and let's say n is greater than or equal to 1, some positive integer, then the Sn, the nth power, is basically all the number of all the elements, which is the product of n elements in S. Okay, so here Si are inside S. These Si may be the same. Okay, you can have the same thing raised to the power n, and it may be all different. But in any case, this is going to be still inside G. That's going to be still finite because your S is finite. Okay. So how fast can this S to the power n grow? Okay, so apparently this may not be all of these Sn, these product may not be all distinct. So this Sn, how fast can it grow depending on n? Well, that's kind of related to the growth function of a group. So we say that it has sub-exponential growth. So we say G has sub-exponential growth. If all of these, if I consider Sn and I raise it to the 1 over nth power, I take the lim sup, that's going to be equals to 1. Okay, it cannot be less than 1, but this is, if it's equals to 1, we say is sub-exponential growth. All right, so of course, if G is finitely generated, sub-exponential growth, you can just check all these generators. And so if you consider the sub-exponential growth, the proposition, the main theorem I want to prove is that they are always amenable. So if G is sub-exponential, then G is amenable. Okay. So the reason is just easy application of the Foner's condition. So let's prove that. So basically, I need to show the Foner's condition. Let's say for every E is finite. Okay, I want to find the Foner's net. Okay, and let's just assume that E is symmetric. I can always add inverse to it. So let's assume E is equal to E inverse, and let's assume the identity is also in E. Okay, and let's fix every epsilon greater than or equal to 0. Let's consider the Ek is essentially just E raised to the power K. And because your identity is in there, so when you multiply something, one more thing, you can always choose to multiply the identity. So automatically you have that your Ek is contained in Ek plus 1. Okay, it's always in there. All right. And I want to show that, first of all, I want to claim that because your lim sup has to be equals to 1, there has to have a k so that this Ek plus 1, the number of elements in Ek plus 1, is less than 1 plus epsilon times the number of elements in Ek. The reason is that if it's otherwise, then each of these Ek plus 1, if it's always greater than or equals to 1 plus epsilon times the previous one, well, then what you can do is that, well, it's going to be greater than or equal to the next one, so greater than or equal to 1 plus epsilon squared times the next one, and so on. So you of course you will have the Ek if you is greater than or equals to 1 plus epsilon to the raised to the power n power k to the first one. Okay, but when you raise it to the power 1 over k, so that's going to be greater than or equals to 1 plus epsilon. So the lim sup is not going to be equals to 1. Okay, so that's a contradiction to the lim sup. Okay, so essentially now I find a Ek plus 1 that's close enough to this Ek. Okay, so there exists a Ek plus 1 that's less than 1 plus epsilon times Ek. So now if you consider what happens for any G inside your E, Well, then the G of EK, if you consider the set difference between EK, okay, well, the G of EK, that's going to be inside your EK plus 1, okay, so it's one of these elements in EK plus 1. So this is going to be less than equals to the, well, do the upper bound, that's less than equals to the difference between EK plus 1 and the EK, okay, so this is just really because this one is inside EK plus 1, so if your X is not in the set difference, then it has to be inside the difference between EK plus 1 and EK. And this whole thing is going to be less than epsilon times EK. I move one copies of EK to the left. I have this less than epsilon times EK. Okay. All right. So basically now I have these kind of fullness condition for these EK. So this is for all G inside E. Well, you may ask what happens if I just take any finite set without assuming it's symmetric and E is in E. Well, if you for every E0 that's finite, you just basically you consider the same kind of you just make it symmetric. You consider E0 union all is inverse, and union is the identity. Okay, and because this is for all G inside E, certainly is satisfied for all G inside the E0. Okay, so all of these fullness conditions will be satisfied. Okay, so this proves that G satisfies the fullness condition, so G must be amenable. And as a immediate corollary, this is probably the easiest way to show that abelian groups are amenable. So corollary, abelian groups are amenable. That's just because all the abelian groups has sub-exponential growth. To see that for every s that's finite, and let's say s is equals to s1 up to sk, and if you consider what happens to the nth power, well, because it's abelian, it's just really what matters is how many copies of S1, S2, and so on you are using. So this is essentially the product of S1 times, say, M1 up to Sk times Mk, where you just require all the power to be greater than or equal to 0, and you let them sum up to the total power is equal to n, okay, because things are abelian here. And how many ways can you divide up n number into a summation of k non-negative integers? That's just a combinatorics thing, and there are many ways of doing the calculation. Well, they may not be the same, but that's just an upper estimate. So this one is less than equals to how many pairs of the M1 up to Mk. You can, well, there's several ways of computing this should be equals to the n plus k choose k minus 1. The point is, this exact number is not interesting, but the point is, this one is a polynomial in n. Okay, so it's a polynomial inside n, and because you have a polynomial inside n, when you raise it to the 1 over nth power, it's always going to be equals to 1. Okay, so the limit, well, you can just take the limit, doesn't even need a limit soup. That's just going to equals to 1, okay, and goes to infinity. So essentially, all abelian groups have to be amenable, okay? That's just because these groups are sub-exponential growth. So we now seen several ways of constructing these amenable groups. So first of all, you can take their quotient, you take subgroup, you can take group extension, direct limit, and all these kind of stuff, you still get amenable group. So here, if I consider a class of group that can be constructed from these known abelian groups and known ways of constructing abelian groups, let's call them elementary abelian groups. So let's use the definition. Let's use EG to denote the smallest class of groups. So it's basically all the collection groups, so that first of all, well, it needs to contain some basic ones. So all the finite groups, well, we know finite groups, when they're discrete, they're certainly compact, so that they have to be amenable. And the second, it contains all the abelian groups. Okay, so we know abelian groups are amenable because they're sub-exponential growth. And this EG needs to be closed under taking basically all these operations we mentioned. So closed under taking subgroup, taking quotient, and taking extension. Basically, you have a normal subgroup, and this quotient is both amenable, and you can build up a new amenable group. Okay, that's called taking extension. And finally, taking closed under taking direct limit. Okay, so if your group can be constructed using all of these finite group and amenable group and abelian groups, and taking the quotient, extension, direct limit, and so on, that's called the elementary amenable groups. Okay, so e.g. is called the set of elementary amenable group. Okay, so elementary amenable group. So apparently, the first question you want to ask is that, well, is this e.g. The entire set of amenable groups? If it is, well, it just means amenability is really easy to compute. But as it turns out, this statement is false. Okay, there are some groups that are amenable, but not elementary amenable. Okay, so I'm not sure if we have time to go through an example, but there exists such a group. And so let's just, so what is in the elementary amenable group? One thing is that every solvable group is going to be elementary amenable. Okay, so every solvable group are inside e.g. so that it's amenable. Okay, so the reason is really simple. So if you recall, what is solvable is that if you consider E and you do the G1 being its commutator group, and you do the G2 being the commutator of the G1. Okay, so you just keep going, and as long as it is solvable, it just means at some point you get some GK that's just equals to the identity. Okay, so that means G is solvable. And the commutator, one nice thing about the commutator is that this G quotient out this G1, and your G1 quotient out G2, all of these quotient by commutator, they're all abelian. Okay, so all abelian. And your GK, your last one, because your last one is the identity, so you kind of go backwards. Okay, the last one is finite, okay, or abelian. So you do the group extension k times, so you get your G is constructed by these extensions of abelian groups. So eventually your G is elementary amenable, so they're also amenable. Okay, so immediately you have G is also amenable, and in fact G belongs these a collection of elementary amenable. Okay, so you have a big class of amenable group just from these basic elementary operations.